All right, this is still 10.1. It is 10.1, the second one. We're going to start with summation notation, also referred to as sigma notation. Okay, it goes by both names because that right there is the Greek letter sigma. So some people call it sigma notation, but what we are doing, what the symbol tells us to do mathematically, is we are summing, we are adding things up. So it is referred to as both summation notation or sigma notation. It also is something that kind of makes us read bottom up. So we start down here. This is our index of summation. It's our variable. It's our counter. If you're in computer science, you probably understand this better than others. But that's just, it could be any letter, that's our counter. Okay, this right here is where we start our counter at. So it's our lower limit of summation. So we're going to, in this case, I equals 1. So we're going to start from 1, and we're going to count until we get to the upper limit of summation, which in this case is n. The general term is what is being added as we go through this. And I can't really explain it much better other than to do an example, because I'm sure that was about as clear as mud. All right, so number 1, find the summation from I equals 1. My eye's got a tail and it's kind of a funny looking eye, but that is I equals 1 to 5, and the general term is 3i. So that means we're going to go through this loop numerous times. The first time through the loop, I is 1. So with my general term, everywhere you have an I, plug in 1. And that's it for the first time through the loop. This is summation, add. And now we come back to our counter and we're going to increment it by 1. So now I is 2. Go to your general term. Everywhere you have an I, plug in 2. That's it for that term. Now we increment I again. Now it's the 3. And you keep going until you get to that upper limit. So in this case, we're going to count everywhere from I equals 1 all the way to 5. So in this case, we did 5 loops. And then just clean up the arithmetic. So and what we have here is simply 9 times 5, which is 45. Number 2, same idea, but we're not starting at 1. Don't have to start at 1. It's going to start at 3. And we're not using I. It doesn't matter what you use. Now, this, and if you use it over here, has to match. But you can use whatever variable you want. So in this case, we're using k's. So we're going to count from k equals 3 until we get to k equals 6. So my general term, 1 plus k squared. Everywhere I have a k, plug in a 3. So 1 plus 3 squared. That is the first time through the loop. Plus, now we increment the k to 4. Plus, summation. Now we increment the k to a 5. And then we do it again and we increment k to a 6. And since that's the upper limit, that's where we stop. And again, just clean up the arithmetic. So I've got 1 plus 9, 1 plus 16, 1 plus 25, and 1 plus 36. 30, 50, 60, 74, 80, 90. All right. Next one. Find the summation I equals 1 to 4 of 3. Now this seems a little confusing because there's no i's in the general term. So what? First time through the loop, I is 1. What do we get? 3. Just a 3. Everywhere you had an I, plug in a 1, but there were no i's. Now we increment the I. Now I is 2. So when I is 2, what do we get? 3. Now we increment the I. Now I is 3. We get 3. And then lastly, I is 4. When I is 4, we get 3. All right, some properties. Here are some properties that you need to know. They're kind of straightforward here. If we have a summation from I equals 1 to n of a constant. Now, it does have to start with 1. From 1 to n of just a constant, it's just going to be the constant times n. That's what we just demonstrated right here with example 3. It went from 1 to 4 of just a constant. We could have just simply did 3 times n times that constant. So the constant's 3, n is 4. 3 times 4 would also have gotten us the 12. So that's the shortcut. As we did, it wasn't that bad. 3 plus 3 plus 3 plus 3, no big deal. But what if instead of the summation from I equals 1 to 4, it had been the summation from I equals 1 to 400? We definitely want to use the property, use the shortcut. Next one over here, all this one's telling us is if we have a summation with a constant, you can just bring the constant out front and multiply it by the results. Do we have one of those? Yeah, come back to number 1. So every one of these ended up with 3 times. I could have just brought the 3 out front in the first place and simply did the summation of I, counting from 1 to 5. So it would have been 1 plus 2 plus 3 plus 4 plus 5, and taking that answer times 3. Again, would have got us the same answer. And then the third one here, it is simply telling us that if we are doing a summation of a sum or difference, it could be minus as well. It's just like doing each one of them separately and adding the 2 results together. So just some basic properties that allow us to do the math. All right. Next, consider the infinite sequence. Infinite means it keeps going forever and ever. It does not stop. So we have A1, A2, A3, A4, A5, it goes on forever and ever. What will be the sum of that sequence? Well, if it keeps going forever and ever and getting bigger, we're not going to get one. But the sum of the first n terms is called a finite series, sometimes also referred to as the nth partial sum. So the sequence itself keeps going forever and ever. But if we only want the first n terms, then we're going to stop, making it finite. Series is telling us that we are going to sum up that sequence. All right, so the sum of all the terms is called an infinite series. Okay, so if we were to do all of them, and the example there is I equals 1 to infinity of a sub I. The examples for this are actually on the next page, so let's turn it over. All right, so number 4. For the series, the summation from I equals 1 to infinity of 3 over 10 to the power of I. We want to find the third partial sum And then we want to find the actual sum. Okay, so part A, the third partial sum simply means the sum of the first three terms. So we're really just doing the summation from I equals 1 to 3 of our general term, which happens to be 3 over 10 to the power of I. So first time through the loop, it's going to be 3 over 10 to the power of 1 plus 3 over 10 to the power of 2 plus 3 over 10 to the power of 3. And as much as you know I generally don't like decimals, we're going to do these as decimals. So 3 over 10, I'm going to write that as 0.3. 3 over 10 squared, 3 over 100, 0.03. And then 3 over 1,000, 0.003. And when I add those up, we get that answer right there. 333 thousandths is the third partial sum. Now, what about the actual sum? So for part B, now we're going to infinity. So it's going to start off all the same stuff we just did. But it's going to keep going forever and ever and ever. Now, you should have picked up from the above example that it's going to end up being 0 point, and now we're going to have that forever and ever and ever, which is what? Simply 1/3. So we do get a sum for this. Now, you're probably asking, how is that possible? Well, it's because what we were adding was a number smaller than 1 that kept getting smaller and smaller and smaller and smaller. If I was adding 5 each time, plus 5, plus 5, plus 5, plus 5, plus 5, plus 5, it's going to just keep getting bigger and bigger and bigger and go to infinity. And we're not going to get a sum for that. But we did in this case. All right, next part. Some of you are going to love this, some of you hate it. Once again, this is a puzzle. It's up to you to figure out the pattern. So you're looking at these numbers. It starts at 10, it ends at 122, numbers along the way, 10, 17, 26, 37, etc. So it's just like the sequences we were looking at before, only there's a plus sign in between each one. But 10, 17, 26, 37, 122, what do you recognize? Well, hopefully you recognize that these are all one number above perfect squares. 10 is one above 9, 17, one above 16, 25, 36, 121 are all your perfect squares. So it's just take that perfect square and add 1. So that would be your general term. We're adding each of these things. So that's what's telling us it is summation. Besides the fact it also told us use sigma notation. Now, since I chose to use i's, it's going to be I equals. But where did I start? Where did my first term start with? What is the perfect square? 3. What did we end with? 11. And it's all those in between. This one was 3 squared plus 1, 4 squared plus 1, 5 squared plus 1, 6 squared plus 1, all the way up to 11 squared plus 1. So if you see that and you see the puzzle, this can be a fun problem. If you don't see the puzzle, it can be pretty frustrating. You just got to be able to play with it. Stay with it. Next one, same idea. If you see it, great. If you don't see it, it's going to be a little more frustrating. Again, my hint is break it down into pieces. 3, 9, 27, 81. 3, 9, 27, 81. What do you see with that? Hopefully you're seeing they are all 3 raised to a power. 3 raised to the first power, 3 raised to the second power, 3 raised to the third power, 3 raised to the fourth power. Well, that was nice. So that would lead towards thinking 1 to 4. What about the signs going negative, positive, negative, positive? Well, we talked about that before as well. That's simply going to be a -1. Now, is it -1 to the nth power, or do I need to do a +1 to it? Well, before we start looking at that, the first time through the loop, n is 1. So -1 to the first would be negative. Is that what we want? Do we want a negative to start with? Yes. So that should suffice. All right. Now, what about the denominators? 1, 2, 6, 24. That's kind of a problem. Well, again, if you recognize it, not so bad. N factorial. 1 factorial is 1. 2 factorial is 2. 3 factorial is 6. 4 factorial is 24. So 1 times 2 is 2, times 3 is 6, times 4 is 24. If you recognize those, you have it. So that would be our answer. Now, some of you may also recognize that since right here, both the 3 and the -1 are to the nth power, you're going, could we have written it as simply -3 to the nth power over n factorial? Absolutely, that would have worked as well. And that is 10.1, the second one.